I thought I would start this session with a why. I think why is very important. Why are you going to spend the next hour and a half learning about debugging? Why am I here to tell you about it? These two really important questions. So I can answer the second one quite easily. So Allinea is the company I was one of the founders of, and our mission is HPC software tools. So it's all we do. We try and make people get more out of their HPC systems and about their own time and so forth. So Allinea DDT is what I'm talking about today, but you may also have seen Allinea Map, which is our performance tool aimed at developers. And there's also Allinea Performance Reports, which is kind of more aimed at a more general HPC user base who might want to just run an application and get a one-page performance report out that says this application is doing really well on this platform, or this application has problems, can you find someone to help me? So across the whole range there, but primarily it's about HPC. So that, I hope, explains a little bit about why I'm here. The question is, why are you here? Why, as HPC developers, are you here? So we're probably all familiar with HPC for rocket science. NASA, your national labs, they've always been involved in HPC for a very long time, putting rockets up into space and so forth. What about brain surgery? It's obviously the next thing. So this is a case that we were working on. We were working with a university in London, University College London, as part of a project that brought together a number of applications from around Europe. It's called Cresta, and that was collaborative research for exascale software tools and applications. So the idea was, let's bring together lots of people doing applications and look at what their issues are for getting to scale. And one of the codes was called HemLB, which is a Lattice-Boltzmann code. And their mission is around aneurysms and modeling of intracranial blood pressures. So brain aneurysms, as we say here, it's 2 to 5% of the population have some, most being undiagnosed. So that means within this audience, there will be some of us who have them, and we don't know who. 30,000 will rupture each year in the US alone, and the odds are not great. But if you discover these things early and you treat them early, then the survival rate will increase. And there are a number of surgical options. And if you look here at the two different kinds, you've got what they call a saccular aneurysm, which is there's this big bubble popping up in the middle at a very important part of the brain, and then you've got more of a fusiform ones. And it's these that are actually the most dangerous and have the tendency to break. And these tend to be formed around a very important area of the brain called the circle of Willis, which is where right at the back towards the stem where it goes out into two things and goes round. And that, essentially, the danger there is the pressure builds up, they burst, and then, strokes and other things will happen. So what can HPC do? Well, as it stands at the moment, you can use MRI to get a good view of what the brain's blood vessel structure looks like. That's roughly a 100 megabyte data set that would give the most important of the vessels, the larger ones. And then if you just want to model what blood pressure is going to be going around there as it pumps around, then it's just complex CFD. HPC's been all about CFD and many other things, but CFD is one of the core applications of HPC, really. And so if you wanted to, when you translate that MRI into a 3D model, it's a 2 to 10 gigabyte geometry. And this is a sort of a screenshot from one of the visualization toolkits of HPC, so in more of the view of a structure that we HPC people will be familiar with. So what's the impact? What could the ability of that problem, the ability to solve that problem, what could that mean? Well, it could mean that you could take an MRI scan of an individual when they need it. Just before surgery, there's been an incident and you need to decide how to operate. So you take an MRI scan, the surgeon puts it into his little supercomputer sitting beside him in the hospital, and it does this calculation and gives you answers in minutes so that he can decide how to operate on you. But that really does require software that's able to go beyond Petascale. And you also need those answers in minutes and not hours, weeks. You also don't want to sit in a batch queue for 7 days. This isn't good. So we can already see that machines can do 20 petaflops and more, and future ones will obviously be able to do far more than that. And that means that beyond Petascale application, machines will be affordable very, very soon, which means the software has to scale in order to exploit those machines and start delivering on visions like this idea that HPC could help in personal surgical situations as such. So we worked with the team at UCL. Primarily, we're using our performance tool to show and discover some of the performance things that they could improve as they were moving on to a new Cray machine that they had access to. So we started with 256 cores, 512 cores, 1024. Everything was going great. 24,000 cores, still good. Suddenly, 50,000 cores, it crashed. And of course, being a typical HPC system, the output you got from a crash was terminated, and thank you, system. That was really useful. What am I going to do? How am I going to fix that? And the developer of this, he came to me and he said, I just don't know what to do now. And I said, well, let's try DDT. You've been using DDT before. Let's try it at that size. He was keen to. What other options did he have? Before we'd had that conversation, he was talking about whether to switch to using a different partitioner. So, he might have moved to something that gave a less optimal partitioning of the data structure, or he could have spent weeks looking over this problem because he didn't really know where it was. Try and fix that by trial and error, or write a new version of various parts of the code, who knows? But all of those things would have taken time. And I think time is one of the most precious commodities that you could imagine for HPC. So if you talk about the results of the HPC work, the simulations you're doing today, you might be talking about a science or something that could benefit society in 10 years' time. If you have a delay now in your project that knocks you back a month, 6 weeks, 2 months, then you're delaying the day when that result comes in. The actual thing, the goal you're trying to achieve, whether that's fusion physics or whether it's neurosurgery. So can you advance the science forward by fixing your bugs quicker? And of course the answer is yes. Your time is more important than the supercomputer time. You've got a finite time to achieve your science before the grant runs out, and you've then got to find the next source of funding. So what we did, we ran the problem at the full size. I've kept some screenshots that have actually, I ran some of this recently on only 24,000 cores because I can make it crash in exactly the same way on a different machine, this time on Titan. So this is what DDT looked like. This is maybe your first look at Allinea DDT. But on 24,000 cores, very much like you would expect a debugger to be able to do for you, showing you your source code in the middle, some variables being shown on the right here, various parts showing the stacks of processes, and a bit of status there, source file listing on the left. But I'm going to zoom in on the areas that were particularly important to this problem because you obviously can't see that too clearly from the back. So my first instinct was to look at where everything is. Where are all the processes at this point in time? Well, on the previous screen, you might have seen a blue line highlighting the source code, which was telling me application crashed and it was at this line, and the processes were at this line. Here, we've gathered together the 17,220 processes that crashed. The other 7,000 were fine. They were all running the same code, but 7,000 went through OK, and the remaining 17,000 crashed. That's the nature of some of the bugs we have to deal with. So they're all started out in main, and they were deep inside Parmetis. Does anyone use Parmetis as a partitioner? Yep, some hands going up there. Great. So it's a very well-used code in HPC. As a partitioner, it's been around a long time. But we're taking this to a large scale. We're taking it to machines well beyond the size that this was capable of, or could have even envisaged when this was being written. I remember working with Parmetis back in about 1998. So Machines have grown a bit since then. So everything, all 17,220 are at this line XYZ part.c, line 556, all the ones that crashed. Well, that's good. So we've taken all the stacks, merged them together in one clear line there saying, this is where they are. Okay, that's the source line. That's line 556. Looks fairly innocuous, fairly simple. But if you get a crash on a line like this, simply assigning mypix bracket I, this is a pseudo-sample sort going on, a random sort going on here, a pseudo-random sort, where it's picking elements from the data set and making a smaller local set of them. So it's mypix bracket I is all pix I times by number of samples divided by the number of processing elements. And who hasn't written a line like that in their life? That's a good way of splitting a long array. Looks okay. So the only things that could go wrong there are mypix doesn't make sense, it's not been allocated. Allpix hasn't been allocated. Or we've gone beyond the bounds of the array on one side of the other or of that. So I took a look at NT samples. And this is a little bit of a warning you may find when first time you start debugging. Sometimes you will discover messages like value optimized out. You may even find you're getting no variables at all. Very important to compile up your code with -g. If you get -g in there, the debugger can tell you far more information. It can give you complete values, such as you're seeing here. Okay, so I recompiled it. I had to actually recompile inside Parmetis library because the user had been expecting it was in his code, but actually it was someone else's big code that he didn't really want to go anywhere near. But simply recompiled it, added -g to the flags, we were ready. So the difference then was we could see that NT samples, that's what we got, 1.8 million, and this is actually being recorded and displayed for every single process in that list of processes that are stopped. So every process has the same value of NT samples, 1818550, NPES, number of processing elements, 24575. That's constant across every processor, every process in this application. Up here, this is just a little graph of the values. So up here, we've got far more random values, like I, on this particular process that we're looking at the moment, it's 2245, but the value is kind of random across all of other processes. Again, nothing untoward there. But then what about I times NT samples? Okay. This is the kind of thing you can come across with scaling. What's happened here, integer overflow, good reminder for myself there. You've got, in this particular case, the default compilation would be to give you 32 bits for integers in Parmetis. There's a flag in a configuration that very few people have probably touched because it doesn't expect that you need to go into 64-bit integers. It didn't anticipate that. It didn't put that as default. So we found that flag then, having realized what the problem was, and the problem vanished. But you have 32 bits. And when your processors, number of processors, for example, is 32768, you've already used a good number of those. I think you've used 15 of those 32 bits. You suddenly start multiplying things together, and you're soon over 32. That negative number is not going to become positive again and put you in the right place. So what it's done is, it's overflown, you've run out of numbers that you can express in 32 bits, and gone and tried to read from a negative array index. And that's not a good thing. So just putting that back in context, you can see I times NT samples, negative number. The rest of the line is divide by NPES, which is a positive number, still going to be negative, still going to be a bad thing. What I found interesting about this is also that only 17,223 processors actually crashed. The other 7,353 ran through that quite happily without crashing, even though they all had that same error. And we can return to that. That's something you can actually detect automatically using memory debugging, which is built into DDT, for example. A deterministic crash is far better than something that might or might not happen. you can fix deterministic crashes really easy. So the more a debugger can do to make it deterministic, the better. So I thought I'd also just do a little pause here to introduce debugging rather than any particular tool. It shouldn't be hard, not if you have the right attitudes. This is by a chap called Robert Pirsig, who's an author on the topic. Having the right attitudes to debugging is hard. We fixed that problem with probably 30 minutes worth of actual brain time. Okay? Now, we did need to get access to the machine twice at a good core count, but these days, 24,000, 50,000 cores, that's pretty easy to get. Give it a week, it'll run through. Or, or even you can ask for exclusive access sometimes. So instead of a long time being taken that could have changed the impact of their ability to provide their science, we fixed it in that time. So the right attitudes is actually being more formal in the way you handle a bug. You're trying to transform something that doesn't work into something that does work. So start having good tracking systems in what you do. Work out a way to reproduce what you do. Work out how to reproduce that bug. Work out how to automate a test case to prove that you've fixed it, and that once you've fixed it, it stays fixed. It's really important to have good test cases in your code. And then you move on, you can find the origin, start to think of where that infection could come from, narrow it down, and then finally correct it. There's two really good books. One is Why Programs Fail, which is really all about debugging. Really, it's just a very good methodical way of going through doing that. I highly recommend it. By Andreas Zeller from Saarbrücken University. He's done a lot of research on the topic. Friday afternoons, for example, are the worst day to fix bugs. Zen and the Art of Motorcycle Maintenance by Robert Pirsig, I quoted earlier. This is based on a study of how traveling across America and discovered how people fix motorbikes. They always take notes of what they're doing. I tried doing this, it didn't work, moved on, tried something else. And yet when we debug, do you take notes? Do you say, I tried this, I tried that? If you do, it will help. But yet, if we look at how people tend to debug in practice, we run, it crashes. We have an idea, we put a print statement in there, we compile, we run, we crash, we hypothesize, we insert a print, we compile. It's slow. And if you look at the types of bugs you might come across, bore bugs, steady, dependable, great bugs they are, the ones you can easily fix. Heisenbugs, ones that vanish when you try and observe them. The Mandel bugs, these are very complex, very obscure. They look chaotic, but they're not. They're real. They have a real cause behind them. I think that's one of the important things about bugs. All bugs have a cause. And finally, and this does happen, it certainly happened to me, Schrödinger bug. First occur after someone reads the code and deduces that it could never have worked, and then after which the program ceases to work. Okay, so let's look at what printf debugging does for you. You would put a line of code, you have an idea, you think it's here. So you put something that, print hello, line 54 of code. It runs, you might not reach that line before it crashes, so you'll go back and put something in at an earlier line, maybe line 20. You'll move back and forth, you're bisecting. Bisecting manually is not a quick way to fix bugs. But when you imagine putting that together with lots of processes, and tens or hundreds of thousands of printf statements all coming out, not necessarily in any order that makes sense because you've got so many processes, it's too much. You could try to reproduce your problem at a smaller scale, but my example earlier was an example that only crashed at high scale because of some assumptions that had been made about integer length, or the need for integer length. And besides, what are you doing running on a very large supercomputer if your program crashes at a small scale? You probably already hammered out most of the bugs at your 16, 32, 128 core things. You might find the system is broken. It does happen. It's not necessarily your fault. Or it could just be probability stacking up against you, and that's happened to me. We had in a couple of examples, one where we'd written some code, and one where it was a third party, one of the system vendors. The probability of a bug was 1 in 32,000, independently on every process. which meant when you tried to debug 32 processes, you'd never see that bug. You'd never fix it. Right? Well, not unless you want to try debugging that like 1,000 times or at least 500 times to get a good probability. Yet, as soon as you tried running that code on 100,000, it crashed every single time. Okay? So sometimes probability will gang up against you, and it means that really you have to debug at the scale of the problem. It won't happen every day to you, but it will happen. It's, especially when you look at the spread of large machines. You know, they're growing. Except for this little this graph line here. This is the size of the number one system in processes, in cores. The number one being the top line on a logarithmic scale, which is the big coprocessor-based thing in China at 3.1 million cores. Number 100, just arbitrarily picking the number 100 out of the top 500. It's tracking upwards. Number 500, well, it's just dropped recently, but that's because in the top 500, you've got a lot of different processor speeds in there. Some systems might be 4 years old and still be in there and have a high core count. And you might have a brand new one gone in with 500, at number 500, that's got a tenth of the processor count of that system. Yeah. So fundamentally, though, we're all trying to get to extreme scale. That's why this course is being run, to enable you to use the large machines and use those well. Look at Titan, nearly 20,000 nodes, roughly 300,000 cores, and almost 20,000 GPUs. Look at Mira, potentially 786,000 cores. You could even have up to 3.1 million hardware threads. So you can't put printf on that. And that's one of the things that both Argonne and Oak Ridge recognized. And that's why we've been working with them over the years to make sure that full-scale debugging worked and was able to actually help them when problems actually arose. And so you now, as users of these machines, as people who are actually going to deliver that science, what you need to ask for is say, right, I want a debugger that's going to work at the scale I'm trying to work at. And wherever it is I'm using, I want to be, the fact that I put a GPU in there, that shouldn't affect it. I still want to be able to debug it. And then importantly, assistance. And actually, the good thing is, all of this is there. So at Oak Ridge, at Argonne, there are people whose job is to look after you and make sure you can actually fix your application and run. There's documentation. There's experts who can help you with debugging. So don't be shy of using them. So let's move on to actually the tool itself, the Allinea DDT. So it's a modern debugger that can cope with pretty much every programming model you can think of. So you've got your C++, Fortran, UPC, SHMEM, Core A, Fortran, and so forth. It's all in there. GPUs, Intel Xeon Phi coprocessors, MPI, OpenMP, just pthreads. It's all there. It's actually got the same user interface as our profiling tool. So when you've learned one tool, you also get the other one, which is kind of nice. So those, as you saw earlier in my example, some of the things that DDT does to make life easy, it gives you the answers to the questions because it's all in the user interface. So where did it happen? Just leaping to the source code. As you saw that blue line showing you where you were in the source code. That's often enough, So that can often tell you the how, just from the source code, but more often than not, you probably need a little bit more context. So the stack traces of all the processors, grouped by what line they're on here. As you can see, 150,119 on this line, one processor on this line. Is that the source of a problem? Okay. But also, you saw the data values being distributed across all, how they're distributed across all processors. This is my MPI rank. It should go from 0 up to number of processors in the job diagonally. There was a bug in the MPI library during that release. And the MPI ranks that they were telling the debugger they had and the MPI ranks that the user's code had were not that straight diagonal line. And that pattern was evident instantly. That's the sort of pattern you would never have thought to have looked for. But the fact that the debugger shows it you is priceless. So you can do a lot of things very, very quickly if you use the debugger. With memory debugging, you can force that randomness to disappear that I talked about earlier. You basically use, under the debugger, you can ask it, protect memory locations above this array, and then as soon as you run and you stamp on, or read even, the element beyond the array, it will spot that. So there's a number of things in there. I couldn't possibly and wouldn't want to talk for multiple hours on all of the features that are in there. Number of things I like to try. I mentioned earlier, debugging at large scale often means you need that access to a machine. You need the 50,000 cores, and you might have a bit of a wait. Well, there's an offline mode where you just run it, and it'll log things. So as a scalable printf kind of solution, really, it merges all the output from trace points through the application, gathers information if it crashes, almost like you would see as if you were running in the GUI. So you put it in the queue on a Friday, come back on Monday, you can understand why it crashed. Setting watch points. Sometimes you'll have a variable that just magically changes. That often happens because you've touched an array element that is, well, tried to touch something in an array, but actually you were beyond the array and in another area of memory that corresponded to a different variable. So it's what you don't expect. These are things you can't fix with printf. You wouldn't expect to have to detect, you wouldn't expect a variable has changed, so you'd never try looking for it. And even if you wouldn't be able to look. So stopping when a variable changes, what they call a watch point, very useful. Even integrated static analysis. So static analysis looks at your source code and runs through it and can detect things before the application has actually been run. There are dangerous things you might do, like not initialize a variable or not free some memory that's been allocated purely within a single subroutine. And so we integrate these by putting little tooltips in the source code there. And they're great little warning triangles. They're not always errors, but they're warnings. They're things you could do better. You could change that, fix that. This one here tells me the portability of a type void star when using void pointers in a calculation is compiler dependent. It's undetermined. That would be a good thing to fix before you move on to a new computer. So, as I mentioned, memory debugging, but also you can detect things like memory leaks, using too much memory and then, crashing your job. Well, memory leaks can be detected. So underneath DDT, there is a scalable tree architecture which enables us to control lots of processes. Now at the top, you've got yourself connecting through the GUI, possibly remotely using our remote GUI. And at the top of the tree, it will communicate with probably a layer of about 100 beneath it. And then there's each of those in the layer talk to 100 beneath those. And so that allows us to send a single command from the GUI saying, play, and then I can set them all playing, or pause. One message goes down, hundreds of thousands of processors get told to do something or report back an answer. When we want to see what variable I is across every processor, or something more complicated that needs calculating right down at the bottom, the fact that our GUI uses a debugger that works right down at that level means we can calculate some very complicated expressions for you instantly and merge back what they look like across every process. But fundamentally, usability is very important. So that's why I've started out looking at the user interface. But it takes, to step 100,000 processors would probably take about 100 milliseconds, 100, 150. And that would actually then display everything, show you variables in all that time. And so that means it's as quick as just debugging a single processor to all intents and purposes. It feels like you're just working on your laptop. Another example, a HPC code at Oak Ridge crashed at 98304 cores a few years ago now, this particular example. Didn't know what to do, didn't know which process to put a printf. He thought it was in a different process every time it crashed. And it was crashing a lot, but he just couldn't keep repeating. So he just put it in DDT, and 30 minutes later, he saw a null pointer on a line and was easily able to get there. This is the offline debugging I talked about a moment ago, where you submit a job into the queue, and the next day or over the weekend, it runs and gives you the output. It's a HTML report that you can just see the whole stack frames merged. So it's just, look at it in a browser, you can see all the information you were looking for. So very good for post-mortem bug fixing. And we've used this, for example, at Argonne with a code that was failing at 16K cores. Access to the machine was very tough because it's very busy. So we just put it in the queue. And then on next week, we looked at it, found a variable was 0 that couldn't possibly be 0. And the developer said, no, it can't be 0. And then we said, yes, it is. And it was. So this is how these things work. Sometimes if bugs were expected, if you knew what the cause were, you wouldn't need a debugger. The point is often you don't know what the cause is. You need a tool to tell you. So I'd like to just do a quick demo of DDT. Okay, so I'm actually connected to Tukey, one of the Linux machines in Argonne. But I could be demoing this on my laptop if I wanted, but I've just decided to go remotely and do it over there. So this is DDT's launch a job screen. Select the application, the number of processes, the number of nodes. It depends on what your system is as to whether you have to choose those. But DDT can be configured to make that easy. And it's ready to submit to the queue. If I wanted to turn on memory debugging, there's a button here to do that. But I won't. I'm just going to go straight in, and run a job I've done earlier. I'll do it on 10 processes, submit to the queue. It's going off. Submitting that, and then we'll give it a moment and it'll start, hopefully. Yeah, there we go, starting. Okay, 10 processes connected, 10 ready. All right, so this is what you typically see when starting a job. DDT starts your job at the, it comes back, returns you control when you get to MPI init. So we just finished there, we're the line just after MPI init. Up at the top, you can see 10 little red boxes, 0 up to 9. These are the individual ranks within your job. So I'll show you this by stepping over an instruction in a moment, but you can see things like the current line that's just showing you the variables that are on the current line, or local variables for the entire application. So let me just drag and drop to show you a few more. I can see variables. This graph is showing me how the 10 processes, how they are distributing argc. They've all got a value of 1. They've all got a rank myID of 0. That's interesting, but then that's expected because we haven't got to this MPI com rank line yet. So let me just step them. So this is what you can do. You make them, the debugger can let you just step individual lines of code just by pressing this step over button, and you'll see them move. And as they've moved forward, so the variables have changed. So you can see now my ID is 0 on my currently selected process. That's a 0 there. It's colored green because it's different on other processes. And you can see that diagonal line, how that value of my ID varies from rank 0 up to rank n minus 1. Okay, so if I switch to rank 8 by just pressing here, you'll see my ID switches to 8 from 0. Oops, just drag that back again. So my ID is now 8 because I've just moved to looking on a different process. Okay, so with the debugger, you can do things like set a breakpoint when you arrive at a particular line. The processes will all stop there, and then you can interrogate them and see what's going on. So to set that as an example, I will just put a breakpoint on this line here. And then tells me that I've hit this breakpoint. Do I want to pause? Yes, I do. And now I can see received equals 0 everywhere. Max is 5 everywhere. I'm sitting on this line. All processes are on that line. Oh, actually, no, they're not. There's still, only 0 has stopped. Let me just pause, see where all the others are. Where are they? And in fact, they're all in, I've got one that's on this line and the others are in here. So they're going to be on there. I must have pressed the button twice. Okay, so we've got 9 processes at line 48 and 1 process here, top of the mouse. Mouse there. Okay, all right. So now I can pause them. You can see that received is the number of elements that have been received by this particular application, and it's 0 on process 0, and it's a different value on the others. I can actually take a look in detail, and now that's detected the value off every single process. 0 has got a value of 0, and there's a value of 1 on processes 1 to 9. Okay, so able to look across variables very easily there. Okay, so this particular code, there isn't really that much to say about it. It's process 0 is sending a value to process 1, 1 passes it on and goes round in a loop. So let's run this right through to the end. all they do is send it around the loop, I think 5 times, and then the process should come to a halt. I pause, because it hasn't stopped yet. This is interesting. Why hasn't this application stopped? It has not stopped because, I hope you can see that down in this area here, I've got some processes are on barrier. In fact, if I look at it, it says 9 are on this line. And the one remaining process is on, it's still on line 48. It's inside pass it on, which is the bit where they pass it to their neighbor. Let's have a look what that's about. Somebody's still at MPI send, and yet all of the others are in a barrier. That sounds like no one's there to receive. So who is it that's there? Top of the mouse. Rank 0 is on that line, and the others have gone off and nearly completed. So I can go up. Oops. Right. And now let's have a look at that. What was the variable we were looking for? It's received and max. Everyone has, max is 5. Everyone should go around this loop 5 times. And yet everyone has received 5 of the packets, and yet process 0 is still inside here, still trying to send it. And it doesn't take too long to discover that process 0, because it put something into the loop, shouldn't be receiving, because there's no one to send it a packet when they've all received 5 times and sent 5 times. Process 0 should stop sending because there's no one there to listen. So you're very easily able to see, using that the values across all processes, they were good, they were consistent, they were what we're looking for. And we could obviously look at all sorts of other things in there. If I wanted to look at particular values, I can just enter them in this box down here and keep an eye on them, that kind of thing. But fundamentally, what this is about is a very interactive experience where you're able to just examine every single variable, cause your application to pause, step a little bit, examine things, and discover what the problems that you have are. So I'll move on from that quick demo back to the slides. I guess people here have access to any number of systems. I just mentioned Titan as one of them. It's all there. It's ready to go. Module load DDT. You're ready to debug. There are many ways that you probably discovered to access HPC systems, and that's one thing HPC doesn't necessarily make too easily. You have to SSH to a machine. You have to make sure your X display is displayed back on your laptop, X forwarding or other systems, and so forth. But there are other ways to do it. So I will just also talk about this one, and it's as we actually have it installed on both Mira and Tukey. You can actually download a local client. So what I was working on and just demonstrating there was actually running on my laptop. This local client is a proper, full native application for Linux, Windows, or Mac. What that brings you is something far quicker and more responsive than you would get through X forwarding. So any network problems, it's far quicker to be using the remote client. And it's far easier to configure. In fact, all you need to do is download the software from our website, install it, and then you run the installation software. It's pretty straightforward. And then when you actually launch the application, launch the debugger, let me just demonstrate this one. So over here, I've just typed in DDT. There's a remote launch that you can configure down here. In this case, Tukey. Well, I'll just show you the configure screen. You have hostname, so it's username at hostname, the installation directory, which I'll show on the slide in a moment, and then you're connecting to the other one. So for Tukey, very simply, it's going to do that. It'll usually ask for you for a password, but I've got a SSH session in the background there. And I'm now connected. All my files are on the remote system. Whenever I want to do any, when I'm debugging and it runs through, it'll retrieve my source file from your remote thing and display it on your laptop. You can actually make it work in the opposite mode where the source code is local and the binary is remote, but more often than not, people have the source code up where they have the binary. And you're back, you're working with Tukey again. Okay, so that's how the remote client works, and that works, and it's been set up very nicely here, and you can just, as I say, download it, and then you should be good to run. So download it, your username at cetus.alcf.alnl.gov or username at Tukey alcf.anl.gov. The remote installation directory is actually common to both of the platforms. It's just soft debuggers DDT, so just put that in the line that's beneath your username hostname. Click test, and you're ready. You're good to go. Don't forget to compile your application at the other side. Then you just select the binary and run. So I'm coming to a conclusion.
So you can refer to Dave's slide, but also there's a web page if you just look in the reference guide, and it's there. It gives you the download path for the remote client and a few more details.
Yeah. So thank you, Ray. As I say, it is a common, the way it works for Tukey, Mira, all identical, so it's very easy to switch between systems there. And it remembers all the configs remotely, so it's actually up on, as in on the supercomputer side. So if yesterday you happened to be in the office in Argonne and were using, through SSH, and then tomorrow you go home and you start using your desktop PC or laptop at home and are doing it, it'll remember what you were doing yesterday. All your settings are there. So it remembers things like breakpoints and things that you set in previous sessions and all the parameters. So my favorite features, if I was looking across what it can do, as I said, I can't focus on them all, but if I was trying to debug at scale, my favorite things are really parallel stack view. We've seen that, how it showed all the processors in the Parmetis crash were on the same line, or here we're seeing something where we're able to detect that processors are doing different things. The ability to detect things you weren't even expecting you needed to detect by looking at variables across processors, that's been critical to finding a number of issues very quickly. You can actually look at arrays in parallel. If you've got an array that's on one process and you want to look at it, that's great. But if that array actually, you've got multiple copies of it or different versions of it on every single process, you might have, say, 100 megabyte array on every single MPI rank, and you're looking for the NaN that is corrupting your visualization or corrupting your whole calculation, then you can ask it. You can say, search for the NaN. It's a distributed array. This is a multidimensional array viewer in DDT. Find me where $ value is NaN. It'll go off and it'll look and return the subset of that distributed array that is a NaN, for example. Or you can just look at values of variables. Even more advanced than that, we've actually worked with the visit toolkit, so you can actually integrate DDT and visit, and you can click on a point in visit, and it will take you back to the process that's looking after that part of the array. And it can tell you things about the memory allocation that you're working with at that point as well. Obviously, it's still very critical to step play and have breakpoints and so forth. You'll notice in my earlier, or you might have noticed in my earlier example, or my latter example, I was showing you the ranks 0 to 10, or 0 to 9, little red boxes showing you the status of processes, so red for paused, green for playing, and so forth. Little red boxes do not scale too well, so you'll notice that the GUI mutated. And at 200,000, this is a screenshot when it was 200,004 processors, you tend not to know your processors individually by name. You don't know process 784 or something like that well. You don't know exactly what that should be doing. So it becomes more important as you scale up to know what they're doing collectively. So in this case, 200,004 are paused, but you might also see something like ranks 0 to 780 are running, 781 onwards are paused, that kind of thing. So that's in there. And finally, offline debugging, that's been very useful when you don't have on-tap access to the scale of the machine that you want to use whilst you're still in the office and ready to debug. Just put it in the queue, let it run, and examine the output. And the best thing about all those features is they're all very parallel, so they do scale up to whatever scale your application is. So in summary, not difficult to debug at scale. It's very similar to just debugging individual processors or a handful of processors with DDT. It's also not slow. You don't be put off by what you might expect. When we surveyed people and asked them, what do you think of the reasons for, or how, what do you think the problems with debugging at scale are? And there's like, well, it'll be complicated, it'll be slow, or that kind of thing, or it won't even work. And in fact, the reality is completely different. So you do have that logarithmic performance, which means you are getting that 100 milliseconds response time on most systems. And of course, this is actually stable in production and well supported. So there's a number of people who've already been using this over the last 4 or 5 years now to debug problems at 100,000 cores and beyond. So with that, I will open for questions and conclude. So any questions? I should also point out that I'll be around in the hands-on and also later tonight, and we'll have some examples and so forth on the Argonne machines for you to play with as well. So very delighted to go around and give anyone a hand who likes any assistance or with your own codes as well.
Do you need any additional setup for the hybrid mode debugging if I want to do MPI plus OpenMP?
No, that should just work out of the box. Yeah, because OpenMP is kind of independent. Once the process is launched, it's all within individual processes, so that's fine.
Yeah. One quick more question: is there any sensitivity in terms of the client version to be compatible with the server version?
Yeah, they need to be running at the same major, or the same. If we have 4.2.1, then your client would need to be 4.2.1. But individual patch numbers, which are basically our minor patch fixes, that doesn't matter. So I think I've probably got a different version than what Ray's got installed on Mira at the moment, for example.
In the offline mode, how much overhead do you normally see for an application running with and without the debugger?
Well, it's close to zero. I mean, debuggers don't really put much of a strain on it. They don't. It's the tiniest. It's kind of microscopic percentage. But there are things you could do to make it slow. If you were putting trace points inside a loop that was called 1 million times, and that was then getting recorded, then that would slow it down. But if you're sensible about where you decide to instrument by that trace point mechanism, then it will fly. You shouldn't notice any difference.
What are the sorts of outputs that the offline mode gives you again?
The offline mode will give you HTML and plain text. The HTML's much nicer, obviously, than plain text. So you just put it in your browser, and you can in the HTML, and you can kind of open up trees and see down into where the stack frames are, and there's little graphics for the spark lines, the value distributed across processes, and so forth.
Are there any limitations in accessing the data? I mean, sometimes I think you need to pin the memory or something like that. Are there any limitations in that regard?
No, not on the debugger. I mean, a debugger.
If it's a particular variable that might change value, can you do it throughout the code?
Yeah, absolutely.
Because I was running into some problems, but anyway, so you are saying there are no limitations?
I don't think there's any limitations, not that I can think of. No, I would say that's all pretty good. I mean, your pin memory is not an issue. You're still able to look at it. I don't know. We'll take that offline.